Okay, then let's start today's lecture. So, hello everyone. Today is the fifth week of the control system lecture series. So, in this week, I hope you have gone through the lectures so that it will be helpful because I am not going to explain everything that are covered in the lecture. So, let's start the first question of the day. Uh, One second. So, the question says, I hope you have gone through the lecture and you know what are the Hurwitz Routh criteria and how to build the Routh array. So, because that part I am not going to explain in like the steps, the procedure. I'll just explain how it's done, why you can lecture, like you can watch the lecture series by Professor Ram. Okay, so the question is, okay, let me explain a simple concept. Like why we need this condition, the criterion. We all know, like for a while designing a control system, while designing any system, what's our primary goal? Our primary goal, I have explained it repeatedly. Our primary goal, being an engineer, the system needs to be stable. If my system is unstable, I don't like none of the performance parameter will matter because the system will blow away. So the first priority, being an engineer, being a designer, is I want my system to be stable. So the criteria for system stability is all the poles needs to be on the left hand plane. So make it clear, the Routh-Hurwitz criteria is to locate the poles. And suppose you have such long expressions, uh, 10, sorry, s to the power 8 plus 7 s to the power 7 plus 10 s to the power 6 plus something like that, and 5 s cube plus 2 s square plus s plus 3 is equal to 0. So it's a very long expression. If you want to calculate by hand the where the pole locations are, it's gonna take you days to calculate. You can't find all the 8 solutions. So for that, what I want whether all my poles are on the left hand side. That's why if I use the Hurwitz-Routh criteria, then I can at least be sure whether my poles are on the left hand side, on the j omega axis, or on the right hand side, so that I will be sure like my system is stable or unstable. It doesn't say exact location of the pole, but it just says whether it's on the left side or on the right side. So keep it like clear so that your concepts are clear. Why we are doing it. Okay. So let's come back to the question. I'll erase this. The question says s fourth plus 3s cube plus 6s square plus 12s plus 8 is equal to 0. So we know the how. So first, let's check the necessary condition for Hurwitz. Does anybody remember what is the necessary condition for Hurwitz? If someone can unmute and speak, Naman or Agam. So, do you remember the necessary condition for Hurwitz that explained in the class? It's okay if you don't remember. I will explain again, but it's better if you remember that. Do you know? Uh, uh, okay, Agam, what's the condition? Okay, first, okay, let me write it. One condition is the all the co the signs of all coefficients. Okay, same. And any other condition? Very good. Very good. So the coefficients needs to be non-zero. These two are the necessary conditions. Then when we form the matrix and all those calculation, that is for the sufficient condition. Okay. So the necessary condition is in this equation we can see none of the coefficient is zero and all the signs are positive. So both the necessary conditions are being satisfied. Okay. So let's draw the uh, Routh array so that so if you remember, you can calculate it simultaneously with me. So this will be okay 1, 6 and 8 and this okay. Uh, does anybody has any doubt on how to write this array, this table? I think it's clear. Like for S4, just the alternative coefficients for 1 and 6 and 8. Then for S cube, it's 3 and 12. Okay. So what will be this coefficient? Can somebody just calculate and tell me fast? It will hardly take few seconds. What is the this value? This value? This okay. Agam, what's uh, okay? This is -2 and this okay 8. Okay. Agam, you need to be little bit careful while calculating. The steps are, I think you have mistaken in the step. This is 1. This calculation is 1. This is 2. Then divided by 3. So if you calculate, yes, you must have interchanged. So the solution, this will be 2 and this will be coming 8. Okay. So similarly for S1, someone else, maybe Hayat or Amrpali or Saurav, anyone else? This value, what is the S1 value? Very simple. It's 0 actually because if you calculate 2 into 12, yeah, very good Hayat. So it's 0. Okay. And here we don't need to calculate, it's already 0. So how to find S0? We can't directly find S0 because here in S1 there is a 0. That's why the 0 will come in denominator. So that will be infinite. So what we'll do, we'll just perturb this value to a small positive value, some epsilon value, which is epsilon is positive. Okay, you can take any value like 0.001, 0.00001, any value, any small value, just positive. That needs to be positive. Okay, then what happens? Then see, now you can see if I multiply, then here it will come 8. Okay, so this 0 is cancelled. Now it's epsilon and it's 8. You can see as we have taken the epsilon as positive, there is no sign change in this in this column. There is no sign change. That's why we can say it has none of the poles are on the right hand side. Am I clear? Because there is no sign change. None of the poles. The conclusion, look at the conclusion. None of the poles are on the right hand side. Okay, but here is a catch. None of the poles are on the right hand side. But can I guarantee there is no pole on the imaginary axis? Because due to the introduction of 0 and the perturbation epsilon, the S square, look at this expression. This, okay, the s square term, if you write it, it will be coming as 2s square plus 8 is equal to 0. Am I clear? So this expression, if you find out, s will be coming as plus or minus 2j. So there are, in this expression, there are two poles on the imaginary axis and two poles on the left hand side, according to our calculation here. Is it clear? Look, look. Here, while we are calculating, all the coefficients in this row, S1, that is 0, right? There is no other pole, so that we can proceed to S to the power 0 column. That's why what we need to do, you will get to know it about little bit later, maybe in the course. Then what we need to do, we need to equate this expression, the above, where all the coefficients are 0, the above expression equate is to 0. Suppose there is some hypothetical expression in S2 you are getting all 0, then whatever the expression S3 coefficient, then S1 coefficient, that needs to be 0. Okay, equate it to 0. Then you will find the poles. So here 2s square plus 8 equate to 0, you find plus or minus 2j. Because S1 coefficient, in the expression for S1, all the coefficients are 0. That is the reason. Otherwise, you cannot apply this kind of trick. Because this S1 expression is 0, the S2 expression, whatever, equate it to 0, and you will find the pole locations. Okay, so that's why two poles are on the j omega axis and two on the left hand side. Okay, in your assignment while solving, you might be getting some questions like this where two poles or three poles might be on the three poles j omega axis is not possible because they exist in conjugate pair. 4 or 2 or something like that, you need to be little careful. It's guaranteed that none of the poles are on the right hand side, but I am not guaranteeing all the poles are on the left hand side. Two poles are on the j omega. So if you calculate in MATLAB or if somebody knows MATLAB, just put this expression. What are the solutions? What are the s values? Solutions for the polynomial. Check out. You might get, I think, plus or minus 2j. One is minus 1 and minus 2. You just check out, note it and check these expressions out, like whether I am correct or not. But you need to be little careful, okay, in your exams also. Hmm? Hmm? Sorry, you, pardon, repeat again, please. Okay, okay. Just let's check it out. Okay, let's assume 2s4 plus 32, okay, is equal to 0. Mind it, the s cube, in the s cube line, everything is 0. That is a catch. If that is not there, you shouldn't proceed like this. Okay, so then what happened? S fourth plus is equal to minus 16. Okay, so s square is equal to plus or minus 4j. Correct? So what is the solution for this root of imaginary? Okay, so it will be not purely imaginary, because if you know the complex number, So what happens is the whole is 2 pi, okay, and the imaginary axis are on pi and minus pi, okay. So for 4 poles, it will be like 45, 45, 45, 45. So 2 poles here and 2 poles here. It will be unstable system. Okay, everything is actually connected, the maths and all. So as long as you go into the concept and you get the feel of control system, na, you will be visualizing this concept. That's why I wanted to take this example so that it will be clear to you, like why this system will be unstable. This 2s square, 2s4 plus 32. Okay. Okay. So I'm going to the next question. This question is very much important, not because of this question. The concept I am going to explain, it's very much useful here, because forget about the question. The question is used. I'll come back to the question. But before that, I want to explain you PID controller. You might be hearing this expression, the controller, PID controller, and everything quite a lot of time. So, what is the controller? Why PID is important? Why what does P controller do? What does I controller do? Forget about the expression, mathematical expression. I will try to give you some practical example and intuition, so that whenever you face some challenge, if you can apply this concept. Okay. So in our basic control system, and any point you have some doubt, just raise your hand. If you can't speak, just type your question in the chat, or unmute yourself and speak. I will explain again and again, but please be mindful this concept. This is very important concept in control system. So in our typical example, if this is a system, what we do, we give some input, which is also called actuation. Okay, forget about the term actuation, and we get some output. This is very basic system. Suppose what we want our system to get some value. There is some reference signal, and I want my system to track the reference signal or to reach the reference signal. Suppose, just example, in winter you want your room to be at some temperature. In summer you are applying some AC, air conditioning, and you want your room to be at 12 to 18 degrees Celsius or 20 degrees Celsius. Okay, that's some reference, and there is some output. There is no necessary the reference and output are matching. So that's why I have explained this using a diagram beforehand, why the feedback is required. So I'll just compare the output and the reference, whether there is some error signal. So this is the reference minus output signal. This is called error. Okay. So this error signal is fed into something like controller. I'll explain this term, why it's controller and what it does. So this is a typical control system diagram. Okay. So let's take one simple example. Suppose you are like the example I had explained. This is a house. Okay. Pardon my drawing. Okay. And you want the temperature inside to be exactly at 24 degrees Celsius. Okay. Suppose it's hot summer out there. You have, and this is my system, my uh, house. So air conditioning is the system support. Okay. The output, and here I want 24 degrees Celsius. Okay. The reference. Suppose it's hot summer. The AC was not turned on before. So it's 35 degrees Celsius beforehand. So this plus, this is minus, and here some block. So the error, what will be the error now? The error will be minus 11 degrees Celsius, because 24 minus 35 degrees Celsius. And if I put some proportional controller, okay, simple, whatever the error is, accordingly my AC will work. This signal is fed into the AC. The more the gap, like if the 53 degrees Celsius, some Registan, some desert kind of situation, and there is lot of gap between the reference and the output signal, then my AC will be more active than the temperature is at 23 or 25 degrees Celsius. Then the AC will be doing less work. Okay, so this, suppose this is Kp, some value like maybe 0.1 or 0.5. So when it's the error now, the 53 degree. So suppose what I want, this is the temperature and this is time. Okay. So initially what my temperature was, it was 53 degrees Celsius. Okay. Here 53 degrees Celsius, and here is the reference. I will draw. Okay, I will put some other color. This is 24 degrees Celsius. Okay. So what happens when the distance is more? It will try to. Okay, the plot will be like this. The more the gap is amplified and fed into the SC, and that will work more. The more it is closer to 24, it works less. Okay, this system will work for this kind of situations. Okay, suppose because I am a aerospace engineer and I work in the drone technology, the modern drone technology, similar kind of proportional controller. Here in that example, the proportional controller worked. Suppose I have a drone. Okay, again, pardon my drawing. Okay, what I want this drone to be flown at certain height of 50 meters. Okay, so this is initially at ground. Okay, and what I want the drone to be at 50 meters. Okay, so here my system, what my system is, let's draw the system diagram. The system is the drone, the height, initial height, the height is the output. What I want, my reference signal is the 50 meters, and let's close the loop using unity feedback, negative unity feedback. And here, simple, let's assume it's a proportional controller. I will just amplify the error, okay, and fed it into the drone. Okay, let me ask, let me know your background. Agam, what is your department? Okay, mechanical. Okay, very good. Hayat, what is your department? If you can speak. Okay, very good. Automobile. And Saurav, what is your department? I guess you're a teacher, professor, kind of. Mm. Okay. And Amrapalli or Raghav, can you speak? What is your department? Okay, electrical. Okay, okay. Raghav is from NPTEL. Okay. So what happens is, when, just know how a drone works is, drone has four motors, four propellers, and we give some electrical signals, and they fly. Okay, fly accordingly, like the motors will be rotating, the propellers will give the thrust, so the thrust is downwards, and that's why the movement will be upward. Okay, and it hovers when the weight mg is equal to the total thrust. This is a basic drone. I am not going to much detail in going much deep into the drone technology. Okay, so what happens is, when the height is 0, initial height is 0, so the error is 50 meters. And suppose I am applying some proportional controller which is 1 or 0.5 maybe. Okay, the proportional kp value. So initially, from when it's 50 meters, it will go up, 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 and when it reaches here, okay, just like in the previous situation, when it reaches here, what happens? The error is suddenly 0. When the height is reached as 50 meters, what happens? The error is 0. That's why 0 into 0.5 is 0. That means my drone doesn't get any more control input. So what happens? Then it will fall down again. Is it clear? Because the error is 0, my drone doesn't get any more signal, like any more electrical control input, electrical signal to fly. The power is gone. That's why it will fall down, and as soon as it falls down, again there is some error, and it will fly, it will try, and again it will try to go up. Ultimately, it will settle at a value which is, it will settle at this value, which is mg is equal to the thrust, whatever the thrust is. Okay, it will hover at this value, not at 50. Suppose this is 40 meters. This value, whatever this value, this is called steady state error. The steady state error, you might be knowing, like you have been studying it, but how steady state error happens, this is the situation. Is it clear? So that's why I can conclude this system cannot be tracked using only proportional controller. Am I clear? If I am clear, then I will proceed and I will get the solution how we can reach to 50 meters. Okay. So what happens is, now what happens, uh, what I will do, instead of only KP, I'll give KP plus KI, the integral term also. So what the integral term does, so you know the integral controller, derivative controller, and proportional controller. Proportional controller, what it does, whatever error it's getting, it will just amplify. It doesn't look back to the previous whatever you have given me, पिछले जन्म में क्या दिया था last उस type का. So it just takes the current value, amplifies it, and give the signal. But the integral controller, what it does, it integrates all the past error. Okay, so suppose the error initially, to reach 50, my drone flew like this, suppose. Okay, so all this error, this is the error value, this red, this part is the error, all is being integrated. Okay, that's why when the drone reaches to the 50 meters height, the proportional controller says, look, I am getting no error, so I can't give any more input. But the integral controller says, I have integrated all the past error. Like, तुम्हारे पापों का सारा कारनामा मेरे पास है. So all the error from the past, that's why it's a positive value. So it will give some input. From the proportional controller, I am not getting any control input because the error is 0. But as the error has been integrated for the integral controller, it has some value. So using KI controller, if I want to reach 50 meters, it is possible. Is it clear? Okay. And anybody else, like Amrpali and Hayat, is it clear to you guys also? Why only? Okay, very good. So if I can reach using proportional controller and integral controller, why I need the derivative controller? Simple question. Okay. So what happens is, what is the guarantee that using this much of integration value, this much of integration error, I will be staying at this? This integration might be more than, like if I need 10 Newton of force, this integration might give me 20 Newton of force. So the drone will be overshooting. It will go up. then my error will be coming, so it will come down. So my plot will be this kind of. So it will go like this. So this is, it overshoot. So that's why it will again come down, and here the positive integration and this is the negative integration. So it will come down and it will settle like this. To reduce this overshoot, and we need the derivative controller. So all combined, the P, I and D controller gives the perfect response for a system. You got the idea why it's done? Okay, so now the PID is no more just equations. You can visualize those things. Why it's happening? That's the aim of the lecture today. Because problem I will solve, but this concept you might not get from books. Okay, that's why. Okay. Let's come back to our question. Okay, there were two questions, so I have divided them. Let's come back to the question. Okay, so the system is given this, and we are need asked whether this system can be stabilized using P only, I only, D only, PI or PD. Okay, similar to the drone example, if the drone is stable for P controller only, no, it's not. I and D, I haven't checked. You can check by your own. And PI, yes, it is stable. And PD, you can check. Okay. Similarly, come back to this question. The system is given as y double dot of t plus 4y of t is equal to u of t. And taking the transfer, what is the system transfer function? G of s is equal to y of s by u of s is equal to 1 by s square plus 4. Anybody has any doubt how the system transfer function I have got? Is it clear? Simple? Okay, cool. So let's draw our most friendly diagram. System, this is G of s. So this is H of s, the feedback, and this is C of s, and the reference R of s, or whatever you can take, U of s, R of s, whatever you like, and this is the closed loop, simple. Okay, and this whole diagram, this is called G star. Like I am taking it, check for your book, whatever notation, and this is independent, called open loop transfer function. And the whole, this diagram, I will take some other color. This. Okay, this is called, this is called closed loop transfer function. Okay, so we have the system, we have the C of s. We need to calculate the closed loop transfer function and check whether the poles are on the left hand side or the right hand side to know the stability. Okay. Okay. So for the first part I will draw here. First part, it's saying only P. So for only P, my C of s will be Kp. My G of s is already what, 1 by s square plus 4. If you have pen and paper, solve it with me so that you will get more from this lecture. Then G of s, and then G star of s is equal to C of s into G of s, which is Kp divided by s square plus 4. Simple. So what is my closed loop transfer function here? Can somebody say? Sorry. So the closed loop transfer function expression will be G star of S divided by 1 plus H of S G star of S. This concept is clear, I guess. And here H of S is taken as 1. Okay. So I'll get Kp divided by S square plus 4 plus Kp. Everybody got this value, this expression now? So what is the characteristic equation? Characteristic equation is S square plus 4 plus Kp. Okay. Now comes the question whether this system is stable or not. Can somebody answer? Anyone? Very simple question. Very good. I wanted this kind of response because in the Routh-Hurwitz, what is our necessary condition? Necessary condition is all the coefficients of the Routh polynomial needs to be non-zero and with of same sign. So here the coefficient of S is 0. So if we want to plot it, so let us, we don't know the Routh's criterion. Then how to conclude it? So simply S square plus 4 plus Kp needs to be is equal to 0. That means S square is equal to minus 4 plus Kp. So where, okay, I will, so S square is equal to minus 4 plus Kp. So here two situations, one is Kp greater than minus 4 and another situation Kp less than or equal to minus 4. Okay. So for this situation, when Kp is less than or equal to minus 4, you will get both the poles. One is on the imaginary axis. And for Kp greater than minus 4, you will get one pole here, one pole here. So this is clearly unstable. And this is, the term calls it marginally stable. But I don't prefer marginally stable. It's kind of unstable because your small perturbation is there, the system is gone. So you may call it marginally stable, but the point is it's not stable. Okay. The for Kp, so we can conclude for Kp the system is not stable. Okay. For Kp, for pure P, it's not stable. So is it clear the concept? If yes, then I will go for I, pure I. Uh, can I get some yes in the chat or okay? Okay, thank you. So let's try for I, pure I. So the second is integral. Uh, so integral the C of S will be Ki divided by S. So the G star of S will be Ki divided by S into 1 by S square plus 4. That means my closed loop transfer function will be Ki divided by SQ plus 4S plus Ki. Okay. So now tell me whether this is stable or not. Just by looking at it, can somebody conclude it? Very good. Here the necessary condition is not being satisfied. The coefficient and of S square is equal to 0. So this is also unstable. Like the system cannot be stabilized using pure integral controller. Okay. Then third comes derivative. So the CFS, controller transfer function, is S into KD. So my G star of S is equal to S KD divided by S square plus 4. That means the closed loop transfer function is equal to KDS divided by S square plus 4 plus KDS. So now, can somebody conclude about this? Whether this is stable or not? Stable for? Very good. That is the condition. You need to specify for KD greater than 0, greater than or equal to, I will write. Yes, very good. It's not greater than or equal to. KD greater than 0, stable. Okay. So using only D, we can stabilize it. So now let's come back to PI. The CFS will be Kp plus Ki divided by S, which is equal to Kps plus Ki divided by S. Okay. So G star of S is equal to Kps plus Ki whole divided by, I'll write it in the other page, it will be better. Divided by S square S cube plus 4S. So my closed loop transfer function is equal to, what will be my closed loop transfer function? Kps plus Ki whole divided by S cube plus 4S plus this Kps plus Ki. So now it's very straightforward. Very good. S square coefficient is absent, so that's why this is also not stable. Okay. So now the PD part, can somebody solve it and tell me before I solve it? KD. So the G star of S will be SKD plus KP divided by S square plus SKD plus KP plus 4. So now tell me, what is the is it stable or not? Stable always or some condition? Okay, Kp should be greater than or equal to 0 and if I, what will happen, this what will happen if I take Kp is equal to -2? Okay, then the denominator will be S square plus SKD and KD is equal to 2. So 2S, this is 2S plus 2, isn't it stable? Then your condition is wrong. Then can you think a bit? Greater than what? Very good. Kp needs to be greater than -4 and Kd needs to be greater than 0. Okay, this is the condition. For this it's stable, so I can say this. Okay, you saw the drone example what I had taken. It was being stabilized by pi, but here this system, this given system, is not being stabilized by pi. You need pd, okay, or pid. Okay. So now come to the second part of the question, which is little bit irrelevant to the this question. So I took it separately. So the question says, if the control system, the closed loop control system, is desirable to have settling time below 1 second and the maximum peak overshoot below 15%. So in the last class, I had explained the second order second order responses, and I had said I I recommend you not to remember anything but that expression. If you remember those expression and those formula, that this question will be for 2-3 minutes. It will take in gate exam. It will you can solve it in 30 seconds also. Okay. So what is the formula for maximum peak overshoot? Anybody remembers? What is the formula? Okay, I'll write. Okay, if you don't remember, try to remember these formulas at least. Okay, pi divided by 1 minus zeta square. Okay, this value needs to be less than or equal to 0.15. Okay, so now it's your task to tell me the value of zeta. For what value of zeta, this value, we can get this expression. Like the e to the power zeta pi. For pi, you can take 3.14. Okay. Zeta pi divided by e to the 1 zeta pi by 1 minus zeta square root over is less than or equal to 0.15. Quick calculation. You have calculator, scientific calculator, mobile, MATLAB open, online calculator. Do it and tell me the answer. I have already the answers, so I can verify it. Calculate and tell me. I am also solving it. It's what is the value of zeta? Okay. You verify this. This answer will be 0.15. Sorry, my bad. 51 0.5169. Almost approximate can be actually approximated to 0.517. Okay. The zeta value. Okay. The damping. So the range of damping ratio. This value, this solution is zeta needs to be greater than or equal to 0.517. Okay. And remember the formula for settling time. What's the settling time? Very simple formula, easiest formula for 2%, 2% margin. Simple formula 4 by zeta omega n. Okay. 4 tau or 4 by zeta omega n. So that will be less than or 1 second. That means my zeta omega n will be less than 4 seconds. 4. Okay, 4 seconds. So what is the question? The real part of pole that satisfies the performance criteria. So you remember the diagram I had drawn in the last class? So if this is the S plane, this is real and this is imaginary, and the poles are situated like this. Using this diagram, you can calculate everything I had said. So if you have the poles, then this is omega n, and this is zeta omega n, and this is omega n root over 1 minus zeta square. Okay, so the real part is zeta omega n, negative of zeta omega n, because it's, I'll just write negative zeta omega n. So that's why the real part is minus 4. Okay, understood the question? So for this lecture, I had these two questions because I wanted to explain the PID concept. That's why I had taken fewer questions this week. So any more doubts you have? Okay. In the question, it's asked the real part of the poles that satisfies the performance criteria. And we have calculated this well, this much, this up to this much. Is it clear, Agam? Okay. Okay. So look at the diagram here. Okay. The poles exist in conjugate pair. I had explained this value is omega n. So the imaginary part is, and that I can write the poles here. The pole can be written as, if this is S1 and this is S2, S1 is equal to minus zeta omega n plus or minus j omega n root over, here I will write plus 1 minus zeta square, and S2 is equal to minus zeta omega n minus j omega n root over 1 minus zeta square. So this is the basic diagram. Okay. So the real part is always, if you know the natural frequency and the damping, you know the real part of the pole, which is minus zeta omega n. Okay. And the imaginary, if the question had asked imaginary, then you need to you have this zeta, okay, zeta, and you can calculate omega n from here, and then you calculate the imaginary part, this. Now it's clear? Okay. It depends on the, if it's on the left hand side plane, then it will be negative zeta omega. If it's in the right hand side of plane, then it's plus zeta omega. So in the next class or some class, I am planning to have a quick MATLAB session so that you will be knowing how to plot and draw the MATLAB classes. No, in the not next class, the next to next class, because in the next class I will be explaining the root locus. So after that, I will be drawing some step responses, some KP, KI, KD, whatever I have explained. That part I will try to include in the MATLAB, and root locus, how to draw root locus in MATLAB, so that you will be getting the feel for MATLAB also. Yes. Okay. In the last class also I had said, so the natural frequency, what natural frequency says is, when my system Okay, how to explain it? Uh, when there is no damping or no, the system has, look, the system has a dying out. Okay, uh, here in this example, look at the S1 and S2. Okay, can you imagine the plot? How the plots will be here? The plots will be kind of like this, the dying out. So if I draw the envelopes, okay, this kind of, this is not actually the correct diagram. I'll draw a better diagram, maybe. Uh, so that okay, this is a exponentially decaying curve. Okay, this curve, the red curve is e to the power minus zeta omega n. Okay, and the part which is oscillating, that is oscillating at omega n root over 1 minus zeta square. Okay, I will come back to what is natural frequency. Okay, let me explain this part first. Okay, this oscillation, this oscillation is happening at this frequency, omega n root over 1 minus zeta square. So when there was no damping at all, if you try to plot, okay, this S1 and S2 are here and here. Okay, then what it means, there is less, this value is less, the real part, negative real part is less. What does that mean? If the negative real part is less, then my plot will be uh, quicker or slower. Like from this dying out will be quicker or slower. Tell me. Hmm? Hmm? It will be zeta omega n is less. Then my question is this, yes, it will die fast. Okay. Uh, 1 second. So uh, it will be. And what about the frequency? Is it increased or decreased? Yes. Just a second. One is e to the power minus. No, no. When the real part is less, the dying out will be slower, na? E to the power. The dying. I also got a little bit carried away. So when the this part, when this is the second situation, S3 S4, then the dying out will be like this, it will be slower dying out. So my plots will be like this, of higher frequency, because now the imaginary part is more. So when the poles come this like this to this value, okay, to the imaginary axis, then there is no dying out, no real, like the negative real part. The system is pure frequency. Now when it comes, when this value then up to this, then there will be a constant for e to the power 0. The real part is 0. So that frequency, the frequency at which there is no damping, there is no dying out, that is called the natural frequency of the system. System को हमने छेड़ा ही नहीं अभी तक कुछ. We have not touched the system. Whatever the naturally it had, it has now. Sinusoidal, pure sinusoid in a pendulum in space, like that. Like if you pendulum in space, what is the trajectory expression? It's sinusoidal. Sinusoidal का Laplace transform बताओ. What is the Laplace transform of sin t? This needs to be at the tip of your tongue. Okay, it's 1 by s square plus 1, or it's omega n, omega, then omega by omega square. Okay, I have given a simple like trick. Like generally I used to, when I was in BTech, I used to get confused for cos and sin. So cos ends with s, so the expression starts with s. The s by for cos, it's s by s square plus omega square. So it's not a unified trick. So I just remembered like this. That's why. Okay. So sine. So now tell me what are the pole locations. S is equal to plus or minus j omega. If I plot here one, so it's the pure frequency. Okay. So you can relate the poles with the frequency now. Okay. Is it clear? Okay. Thank you. Thank you very much. Thank you, Agam. Thank you, Amrapalli. Thank you, Balkiran. And thank you, everyone. So have have a great week ahead and good night. Thank you. Thank you.